In this video, we're going to look at the role of GABA A receptors in anxiety. You may remember, if you've seen one of my other videos, that there's this idea that the amygdala controls learned fear and plays a major role in anxiety. The amygdala receives cortical inputs, and these cortical inputs then are processed within the amygdala, but we also have these inhibitory neurons which turn down the amygdala, and that reduces the anxiety. These inhibitory neurons contain receptors to GABA. So if we imagine release of GABA from these inhibitory neurons, GABA is gamma amino butyric acid, and it's one of the main inhibitory neurotransmitters in the central nervous system. So GABA is released, and that binds to receptors. These receptors allow the influx of chloride ions into the cell, and that causes a hyperpolarization. In other words, an inhibition of the neuron. So let's have a closer look at these GABA receptors then, shall we? The GABA receptors are made up of 5 subunits arranged around a central pore. I've drawn this very badly, so I'm going to draw this again. So if you imagine, got the membrane, you've then got your receptor, which is a ligand-gated ion channel, has a gate here, which of course is normally closed. GABA lands on the receptor, it attaches to a binding site, and then when the GABA binds, then this gate is opened, and so chloride ions, which are negatively charged, these can then enter the cell, and so the cell membrane is then hyperpolarized and inhibited from firing. So this is looking at it from the side. If we look from above, we find that this channel is made up of 5 subunits in a ring. And each subunit can be alpha or other beta, etc. subunit types. Most important ones being alpha and gamma. And what's particularly amazing about these receptors is that they contain not only the binding site for GABA, but also another binding site for benzodiazepines. So benzodiazepines are things like Valium. They also have a binding site for barbiturates. They have a binding site for certain steroids and others. So they're actually quite a complicated molecule, and what we're going to look at now is how things like benzodiazepines affect the receptor. So let's start with a new page, and let's imagine we have a receptor in the membrane. We have GABA, and the GABA binds to its binding site, and that will result in a hyperpolarization in the membrane potential. If instead of GABA I add benzodiazepine, this time if I just add benzodiazepine, nothing happens. I don't see a response. But if I keep the benzodiazepine on and then I add GABA, what I find is I get a response again, just like before, but now it's much bigger than before. And the same actually happens for barbiturates as well. So what they do is they allosterically enhance the size of the GABA response. So if we now go back to our model of the amygdala, if now we add benzodiazepine, then suddenly all these neurons are going to become much more effective, because although they release the same amount of GABA, then you're going to get a bigger response because of this allosteric potentiation here.